So we're going to spend one more lecture on simulation, then basically trying to fill all the holes that we haven't solved in today's lecture. So next week is spring break. There will be no lecture. Then after that, we're going to come back to architecture and we're going to talk about how a CPU core is built. Okay, but this time let's finish the simulation part. So I think last time we were talking about smart ticking, right, and how to write this type of like regular components for Akita. Then there are some problems that we haven't solved. For example, the secondary events. So we haven't talked about secondary events. So why we need secondary events? It's not very complex. It's basically the same reason as last time when we were talking about the pipeline, how we implement the pipeline, and why we need to write the thing that happens last, that to make it execute at the beginning of a function. So for secondary events, just consider there are 3 ticking events, right? There's two components and a connection. There are 3 ticking events, A, B, and the connection itself. In hardware, you can consider there are 3 combinational logics, right? Controlling 2 set of registers. The registers are buffers within the port. Then in a simulator, they can execute in any order. So we're executing for example, in a way of A first tick, then connection tick, then B tick. In this case, in cycle 1, A will create a message in the buffer. Then connection will move it to the destination. Then B will take it and consume it, right? So there's a problem that we're receiving the message at the same cycle as we send it. This is something that shouldn't happen in real hardware. So we should prevent this from happening. So how to solve this problem? And the solution is easy. We can simply make the event that delivers the message always happens later than the event that consume messages. So what's the event that delivers the messages? There are basically the events that are happening in the connection, right? So in that case, we set the connection to be a secondary ticking component. So its event is always scheduled as a secondary event. So if events that are scheduled at the same time, if there are events that are scheduled at the same time, we always first execute the primary events, then we execute the secondary events. In that case, we prevent this behavior so that if we can guarantee that connection tick is always executed later than A and B's event. So assuming here A and B's tick, that we can, no matter what is the order, but when A's tick and B's tick is happening, A will create this message, but the connection will not deliver it. Then after that, this is secondary tick, then connection's tick will deliver it. It's still in cycle 1, but since B has already ticked in that cycle, it cannot tick again, it cannot consume. In that case, in cycle 2, B's tick, then it will receive the message the cycle after we send it. Then we have solved this problem. Okay, so that's why we need a secondary event. Any question? Why have duplicate this part? No. Probably accidentally copy-pasted a slide. It's okay. Okay, the secondary event is rather easy to understand. It actually creates some performance issue, especially for parallel simulation, because we have to first execute the primary event, then secondary event, right? So it's something annoying that we have to add actual synchronization between the primary event and secondary event. Now, another thing that we haven't talked about is builders. For every component or many things in the simulator, we use a builder to instantiate a class. Now, what are builders? So builder, let's still look at ROB as an example. This is ROB, it's builder. Now, builder can build or instantiate reorder buffer components, right? So this is the builder as a struct. Then there are some properties of a ROB. as properties here. Then make builder is a function that instantiates a builder. It never takes any argument, but it provides the default value. For example, frequency we default is to be 1 gigahertz, number of requests per cycle to be 4, buffer size to be 128. Okay, so those are default values. If you don't set it, this will be the value used in ROB. Now here, there's a convention in Go. So when we say make something, we should return the value itself. If we write new something, it should return a pointer to the thing. Okay, so it's just a convention that we say we make builder. Now after make builder, we create many with functions. It's always started with, and it's a with something. For example, with frequency. Frequency is a given value, then we simply set it to be its property as a setter. Okay, so with function, you can see with engine, with frequency, with request per cycle, with buffer size. Basically one property, one with function. And these are with functions. Finally, we use this build function to set up the necessary things. For example, we need to say transaction is a linked list that we have to initiate. This is a map, we have to make it. Then buffer size, and the parameters, now we have to assign the parameters. And for ports, we also need to instantiate the ports. Okay, those are all parameters regarding this component. Then, this is how we use a builder. So here you can read it as if it's English. Reorder buffer make builder with this engine, with this frequency, with this buffer size, with this request per cycle, and eventually we build within this name. Okay, so we can write it. If it's not too long, you can write in one line of code, but typically we change lines in this way. So it's rather easy to read, easier to understand, and then you can see how we set up the variables. This is a builder. Then this is a very common type, a common method that we use in Akita. So since we're talking about builder, builder itself is a pattern. It's a program pattern. Then here I also want to talk about the strategy pattern. It's probably the most important. The most important patterns that I find is most important. I really like this pattern. So what is a strategy pattern? For example, in reorder buffer, we have an engine, right? So basically we're saying engine is a dependency, right? So this is the same figure as the dependency inversion. And this is a particular pattern that can help us to implement to follow the dependency inversion principle. So this is an engine, right? And the ROB depends on engine, and we depend on the interface. So we also say this is a strategy that ROB uses. ROB requires an engine strategy. And in this strategy, we know, okay, this is a strategy category named as engine. And what are concrete strategies? We have a serial engine and we have a parallel engine. And there are different strategies, concrete strategies that we can use. Right? So at the configure time, or at the time when I call a builder, we set up which concrete strategy that we want to use. So this is a strategy pattern. It's rather easy to understand, but it's actually very commonly used. So if you find this one is a little bit hard to understand, let me introduce another example. For example, a cache requires a replacement policy, right? A cache requires a replacement policy. Then if you have never learned program pattern or program principles, you would probably write some code like this. Well, there's no chalks. Where are the chalks? Super teeny pieces. So you may write some code like this. If policy equals LRU, then you do this. And then else if policy equals random, you do something else, right? This is a very common way to write these type of things. And this is a bad type of, like we call it code smell, right? This is a typically, if you see this type of code, it's suggesting that your code is kind of not flexible enough. Now it actually violates the open and close principle. We'll talk about that later. But rather than using this way, we would simply do cache dot replacement policy. I will just write RP replacement policy dot evict. Okay. Then it will tell us which one to evict, and the implementation is within this RP. Now it's really about which one you want to use. You should use the builder to set up the right eviction policy that you want to use. Okay, so then we say we need to select the policy when we build the code, right? When we configure the code. So that is another pattern. This pattern is not the traditional pattern. It's not in the design patterns book, but it's a commonly used pattern called dependency injection. I think many of you probably have heard of this name before. This is a common name. So how it's used in Akita and GPU sim, you can see I have two different ways to write this code. First is new cache. When implement a cache, I create a policy and I write LRU policy. Now, if you write this type of if-else code, you don't even need a policy, right? Now here, we're saying in this way, this new cache takes a policy field. And we first create a policy, then we create a cache, and then create a new cache, which is we give it a policy. So what is our dependency? Cache depends on replacement policy. So cache, the replacement policy is a dependency of the cache. Now what is injection? So in this way, we call this self-defined dependency. So we give it our own, we provide our own, or the cache creates its own policy, its dependency. On the other side, we provide the dependency externally, right? We provide the dependency externally, and this is called injection. Injection means we provide it from external and we put it in, right? In this way, this new function, or sometimes as a constructor in other languages, can somehow serve as a dependency injector, right? So this is a dependency injection pattern. Then here, in our case, this is our dependency injector. So builders are dependency injectors. So we inject the dependency using this build function. Okay, then those are parameter setup. You can also think this is a parameter setup, but this is a dependency injector to provide the dependency that the component wants to use. Now we say dependency is more flexible because we can easily change it externally, right? Now since we're talking about open-closed principle and design principles, then open-closed principle is the most important principle. And I would say all other principles are there because we want to achieve open-closed principle. So what is open-closed principle? Is as software entities should be open for extension, but closed for modification. Or in another way, understandable way to say this term, to explain this term is a software entities, a class or function or whatever you want to write, should allow its behavior to be extended without modifying its source code. So for example, here, if you write this type of implementation, if we suddenly want to write like AI-based policy, right? How we can do it? Then you would continue to write it by providing another elif, right? Then this is modifying the code. So why we don't want to modify the code? Because the code is there, it's already working, and you don't want to modify the code, then it's very likely to break it, right? So you want to prevent modifying existing code as much as possible. but you want to add new features. We keeps wanting adding new features. Then when we want to add features, we want to write a new piece of code rather than modifying the code that is already there. So how we can do that? Then strategy patterns can help, and other patterns can also help. For example, in strategy pattern, we have LRU, we have random, but we can implement something new, right? Now, if we write something new and use the builder using dependency injection, then we're modifying the behavior or extending the behavior without modifying the code, right? We're not modifying the cache code. We're simply providing another piece of you write another file, then it's good enough to support this feature. Then, so following this pattern, then, or following this style, then typically I consider my code to be three types of code. So first one I call it data. Right? What is a data? A request is a data. Event is a data. Then a component itself, if you consider middleware, then I'm not saying middleware, I'm only saying the component itself is data because it records the state of a component, right? Then those are data, pure data. Then we should minimize the behavior as much as possible. It should be pure data or state representation of a component. State representation of some state of your program or of your simulation. Now, what is behavior? And behavior, you can consider engine is a behavior, then components middleware, their behavior. Now, those are behavior. Then eventually we have glue code. Glue codes combine everything together. Now, what's our glue code? They are typically like builders or different type of builder, or the code that calls the builder, or even the main code, main function. They are considered as glue code, and they just combine different things together in a way that you are expecting. Okay, so three type of code that is in MGPSIM. For every piece of code, I'm pretty much sure it can be categorized in one type of the code in MGPSIM and in Akita. Then, sorry, I'm trying to finish all the patterns that is related to MGPSIM and Akita as quick as possible. So I'm really rushing the patterns. There are lots of patterns. So then mediator pattern is another very important pattern. What is a mediator pattern? So mediator pattern is a pattern that defines an object that is a behavior object that controls all other states, what the other states are doing. So for example, just consider this is a message, okay? Then my middleware will read the state of the message, read the content from the message. Now, if this is a read message, then what I do is I will change the state of my component. Okay, if this mediator is a middleware, I will change the state of the component. At the same time, I will create another message as a response and send back, right? So a mediator is a pure behavior component or pure behavior code that controls the state of other components. Okay, so then in this way, we should try to avoid mediators to work with another mediator, right? So this mediator should only directly work with the state and read the state and take some input state and generate some output state. That's what the behavior should, that the mediator should be doing. So that also map back to this behavior pattern, right? This behavior type of code, I consider they are mediators that take some data information from one side and modify some information from the other side. Now this is actually very useful because whenever I have unit test, I don't need to test the messages. I don't need to test the component state. I only need to test the mediators. I can see if I give it a state in this way, does it really modify the state of this component, of this element in the desired way? And if it's actually creating responding messages, right? So I only need to test the mediators and I don't need to test all other parts of the state. Right? I only test the behavior, and I don't need to test the glue code. So for unit test, I try to have full coverage on the behavior part. I don't need to test the data, and I don't need to test the glue code. Okay, so we can have a quick review of all the patterns, not all the patterns, all the principles that we have learned. We still have one more pattern to introduce. So when we say principles, we consider solid. There are a few other patterns. For example, do not repeat yourself. Right? There are other principles like do not repeat yourself. This is called dry. Do not repeat yourself. This is another principle, but this is a relatively easy principle to achieve. And for solid, we have learned SOLD, right? What is S? S is single responsibility principle, right? We want to have for every class, we wanted to have one and only one responsibility. For example, here, if you have each state as one class, then it's naturally only have one responsibility. And if it's a behavior, then it will also only have one responsibility. And especially if you try to separate the policies from the main behavior, then each policy or each strategy, like our LRU strategy or random strategy, then it's not almost naturally you can follow the S principle, right? The O principle, I would say O principle is the most important principle, is open for extension but closed for modification. You can you can add features by writing new code but not modifying existing code. Right? That's the O principle. L, we haven't talked about L. Then I principle is for interface segregation. So why we want to do interface segregation? We want to have each interface to be as small as possible. Then for each component, whenever you have a dependency, you only depend on the minimal part of this component of your dependency, right? Why is that? Because if you depend on fewer functions, it's easier to replace it, right? If you depend on many functions that I don't even use, you may probably have to implement something that your dependency, your main object is. You may have to implement some other functions that you don't depend on. Then finally is dependency inversion. Right? Dependency inversion is almost tells you that you should never have a mediator that directly depends on another mediator. Right? You should never have a mediator that depends on another mediator. You should have a mediator depends on interface, then that interface is implemented by other mediators. Then in that way, you can always replace the strategy you want to use. So the overall goal is eventually O, right? I can replace whatever I want without significantly changing the logic, the real logic code, but I can change my behavior in the glue part, in the glue code part, where I build this whole component, I can change to whatever I want. Okay? So then one thing that you probably have seen the code about hooking and tracing. So that's probably the biggest part we have to introduce. It's a big part in Akita. So why hooking? So as you have seen in reorder buffer, when we implement the reorder buffer and even implement the of the engine, right? We focus on the main logic. I don't want to try to write a lot of code that is not essential in our program, right? So sometimes we want to record the data. For example, record what events have been executed, what messages arrives at a port, or what happened, what the instructions are executed in a core component. So those are tasks of recording data, right? So what data I want to record? It's hard to say. And then this time I want to record this data, next time I want to record that data. Now, an easier way is to add print. Then when you add a lot of print, it's violating O, right? When you add a lot of print, if I want to record some new data, then I'm modifying my code. So sometimes some ad hoc print is okay, but sometimes if you want to formally support some feature by recording some data, this add complexity to your code, and your code will eventually become messy and your function will become very long. You don't want this to happen, so we use hooking to separate the concern of logging the instructions and the execution of the instructions, right? And many other things that we can log and trace. And sometimes we want to modify the state that is not part of the regular logic. For example, in a very specific type of research in computer architecture is called fault injection. So we have talked about, say, the cosmic rays may hit your CPU and may make one bit flip from 0 to 1 or 1 to 0. Right? In that case, that's definitely not the real logic that you want to do. You want to implement in your code, and you don't want to write if fault injection, then select a random bit and flip. You don't want to write this code because this is a very rare, very corner case that you want to simulate. So what we can do, we can implement fault injection as another piece of code that can somehow manipulate your state, right? So those are special cases that we want to do, but we shouldn't implement in the main logic. Then we use hooking. So consider this is the main thread that we're executing, and hooks are something that if we want, we hook onto it. If we don't want, we just take it off. Okay? Then it can be attached to this main thread and to take some actions whenever something happens. There is another pattern. This is probably the last pattern that we have to introduce. There are many, many patterns, but we only introduced some of them. Observer pattern, or sometimes this is even called subscriber pattern. If you want to call it a hook pattern, it's also okay. People will typically understand. So I find this diagram online, and it's very concise and very easy to understand. So here's a subject. Subject is our main component that implements the main logic, right? Then we have an observer interface. Then there are some observers that implement this interface. They simply implement an update function, right? It's a very simple update function they need to implement to take the action of this observer. Then the subject should have an observer list that maintains who is my observer. Then it should allow register observer, provide an observer which simply adds to the observer list, or remove observer. Now in Akita, we don't even need to remove it. Once it's on, it's always on. Now the most important function here is notify observers. At the right time, we need to notify the observers that something has happened. Okay, so then these observers allow us to define this behavior at configuration time. If I want to do fault injection, I can attach this hook. If I don't want to do that, just not to attach it at the execution time, at the configure time. So when I say configure time, is basically when you start a piece of program, you first construct the hardware that you want to simulate, the benchmark you want to simulate. Now when you call engine.run, you're actually doing the simulation, right? So engine.run is the real simulation. At the beginning is the configuration code. So what is the implementation of a hook? Then it's actually very simple. It takes a hook and interface, and you only need to implement something called a func. Then it takes one argument that is called context, hook context. What is a hook context? There are 4 things in one context. The domain is the hookable, is the component, the main component. Okay, I call it hookable. We'll see how hookables are implemented soon. There's a position. What is a position? We can name these positions in this way. These are kind of like global variables or global constants, right? So those are positions. So sometimes I may say this is a hook post before event, before this event are being processed. Hook post after event. These are after this event, this hook will be triggered. So this position will tells me if this is something that I may be interested in. Item is the thing that you care about. For example, if you care about an event, then that event is the item. Okay, if you care about the instruction is the item. So this is about what you care about. Then detail is basically whatever you want to attach to this hook, so that you want to attach this to this context so that the hook may or may not need to process the information in detail. You can attach whatever data you want there. So hookable. Hookable is the main component that can take a hook, right? So it takes there are three methods. Accept hook, we take a hook. The number of hooks, the hooks is basically returns all the hooks that are registered. Okay, so here is and also another important function is invoke hook. Whenever we call invoke hook, the implementation is super simple. It's basically just iterate through all the hook list and call this function, call the func of the hooks of the hook. Okay, so notifying the hook, okay, this happened, then do whatever you want if you're interested in it. Now how we call this one, how we call a hook, you can see this is the engine, right? The engine run function. Now when we get this event, we create a hook context. In this hook context, we have a domain that is the engine itself. We have an item that is the event. Then the position is hook position before event. And this is triggered before the event happened. Then we invoke hook with this context. After the event is being handled, we do post, hook post after event. We're reusing this context, but we're just changing the position, then we invoke hook again. Okay, so I would call this thing, whenever I write a hook, this is the observable behavior, right? So at this point, this event being executed is observable because you can attach a hook to observe this behavior. Otherwise, your simulation will keep running, and you cannot grab any data out of this main running thread. So those are when you write a piece of program, when you write a component, you need to consider which part is observable. If you want this thing to be observable, leave a hook there. Then eventually it can be consumed by a hook and to extract this type of information. Then typically whenever there's something started, for example, the start of an instruction, the end of an instruction, the start of a transaction, the end of a transaction, those are all observable actions or observable events. Now we'll leave hook positions so that hooks can monitor those behavior. Okay, then a minor thing is this code may have some performance overhead, and actually the performance overhead is even not very small, not really because of calling the hooks, but mainly sometimes this thing, Go is a little bit different from C or C++. In C or C++, this is something that is typically allocated on stack, but Go may allocate it on a heap. So if it's on a heap, it may need garbage collection. So allocating memory and garbage collection can take a lot of time. So it's one of the positions that we may look at performance improvement opportunities. So, yeah. Okay, then we just want to see one example of an event logger. So event logger is a hook that can be attached to an engine. It's only interested in this invoke hook, this function, that hook post before event position. We only care about this position, and whenever we execute this hook, we just simply print it. It just tells me what events are being executed. Okay. So let's see how we implement this one. So we say this is an event logger, right? It's a struct now with a log hook base, now which is basically take a logger. Then in the main function, in the func, it takes a context, right? And in the context, we first check if this position is something we care about. If it's a position that we don't care about, we return. We don't do anything. Then we check if this component, if this item is an event or not. This is a casting, down casting syntax in Go. So we're casting an item from an interface type to an event type. So if it's an event, if it's not an event, we return. This is not something we care about, we return. Then finally, we print it out, right? We print it out. It just say if this event handler is, if it's a component. If it's a component, we record its name. If it's not a component, we don't record its name. Okay. So it's just a little bit more flexible, but basically it's a print. We want to print this. What's the event? What's the time? Right. So this is a very simple, the simplest hook that we have implemented in Go, and how we can attach this hook onto an engine. So here we implement in this way. You see an engine, right? We create an engine. If user wants to use parallel engine, we create a parallel engine. Otherwise, we create a L0 engine. Then we attach a hook. We instantiate this event logger and we attach it to the engine. Then this engine attached with this hook, then all the events will be printed. Now your whole program will execute really slow because print adds a lot of performance overhead. Okay, if you print to a file, it's probably okay, especially if you print to a terminal, it's 1,000 times slower than without printing it. But sometimes it's just a debugging mechanism. So I typically will keep this line here, but for most of the time, I just comment it out because I don't want to see this type of events being printed. Okay, any questions so far? Event logger. Okay, let's move a little bit forward. That a special type of hook is in the tracing, is implemented in the tracing package. Then basically in the tracing package, we don't care about events, but we care about tasks. What are tasks? You can consider each task contains 2 events. A task, event is always a single time, like an immediate thing, right? Happens at a single time, a time, then there's no duration. That's an event. Now a task is a pair of events that something started and something ended. For example, I execute one instruction when I started to execute this instruction and when I'm done with executing this instruction. So a task has a start and end time. And also, if you look at the fields here, what are the fields here? There's an ID, identifier of this task. There's a kind and what that depends on, that describes what task it is, right? A kind is a category, what is a description. I really want to name this kind as type. Then later on, I realized type is conflicting with the type keyword. So now I have to name it as kind. Okay, so kind, what, where. Then I have only one where field. That means one task can only happen at one position. Okay, so one task can only happen at one location. If you think, oh, an instruction may need to say, oh, it needs to be executed here and pass to that position, then being executed here, then pass a few different places, just consider they are different tasks. Okay. Then the most important part is the start time and the end time. Then steps are basically we currently use as tags to this component, to this task. Then we will see how it's used later. Detail is part of the information that is you can attach to a task. Later on, it may be useful or may not be useful. Then parent task is the most interesting part. Now we say we find this is a super simple implementation that eventually it enables a lot of things. So the parent ID field or the parent task, we don't really have to enable both of them. It really depends on if we want to serialize into a JSON format or store it into a database, we probably only want to keep a parent ID. If we want to use it, we probably can directly keep a reference to the parent task, right? As you can see on the right side, this gives the instruction about how to serialize it into a JSON format. Then, whenever we have a parent task, the parent task may have another parent task. So using this parent task, your whole tasks of your program execution forms a tree. If you consider our root task is called simulation, right? It's called simulation and may always have an ID of 0. Then in that case, that's the root. Then all other tasks are leaves of this root. Okay, then it will make, we start to understand the whole execution as a whole tree of a graph that we have to execute these tasks in our simulation, right? Then we provide special APIs for handling tasks, but they're basically wrappers for hook invocations. Okay, so we have a starting task. We start a task with an ID, with a parent task ID, with a domain. It's a named hookable. It's a name and a hookable. Right? It's a combination of two different interfaces. What's the kind, what's the type, what's the detail? If you want to attach detail, for most of the time, detail is new. When we start a task, we call this function. When we end the task, we call this function. Then for end task, it's super easy. We only need your ID and the domain, then so that we can map with the original starting task, right? If we can map with the starting task, we know the end time that's good enough. Then we can store it. We can save it somewhere. So this is the end task. They're nothing special. They're wrappers for invoking hooks. Okay, so we'll create a task. We'll create a task struct within this start task and the end task function calls, and those are items, right? And this domain named hookable are the hookable that these domains in the context, and the position is always something like task start and task end. Okay, so it's not something just dedicated code, is just wrappers. Then a very special thing of a task, or the most common type of task, is when we're handling requests and handling responses. Just consider a core sends a memory request to a cache. Then this is a task, right? This is a task that starts at time that when this request is first created or first time it's being sent out. We typically consider when this is created because sometimes it may buffer in itself, wait a little bit before sending it out. We want to record the earliest time as the earliest possible to record when this request is relevant. Right? So the start time is when this request is created, and the end time is when this response is received. Right? We consider this is a task. This is the time that it takes for a whole memory transaction. Recording the end time and minus the start time is the duration or the latency of this memory transaction. Right? Then this task, consider this request is sent to a receiver. So this is at the cache side. On the cache side, when we first realize, okay, there's a request, it's the task when we receive this task, right? Is when we retrieve from the port. So this time is when the request is received. So it may be buffered outside this component for a little while, or if there's a network that takes some time to send this message to the destination. Okay, so there's always a small gap here between the start of the parent task and the subtask. There's a small time. And it may take some time for the cache to either it's a cache hit or cache miss, and it may take some time to process it. So eventually this task is completed. We have the data ready. Then we can send this data back to the requester. Now it takes a little bit more time. That may be buffered at the requester side, or the network may take a little bit time to deliver the response. But this is another critical time, that is the request, when the request is completed. Okay, so we just give it a kind. This is a request out. We send out a request. And this is a request in. We receive a request and process it, respond to this request, and process this request, right? Then we always point a parent task. This request in has a parent task of this request out. And so one request, two tasks, right? Because this request has two different locations. One request, two tasks, and 4 critical data points. We provide specialized API to handle this. We name it as initiate. Is when is first being relevant is initiate. And when it sends to a destination is receive. When it's completed is complete. And when it's finalized, it's finalized. Okay, so 4 simple APIs to record the life cycle of every request. Then still, there are wrappers around start task and end task. So 2 level of wrappers, right? These are wrappers of start task and end task. Start task and end task are wrappers of hook invocation. So we provide these 4 convenient APIs to handle this request out and request in, this type of specialized tasks. Then finally, tracer. What is a tracer? A tracer is a hook that cares about tasks, right? So we say whenever we call those API, these APIs are eventually wrappers of hook invocations. So then we need specialized hooks that care about those tasks, right? So then we need to write a tracer. The tracer is also very simple. It only needs to implement 3 functions. One is start task, one is step task, one is end task. Step task means it's executed in the middle, and if there's some extra information need to be recorded. We only use it for one purpose right now. It's in the cache to record it as a cache hit or a cache miss. Because at the beginning, we don't really know it's a cache hit or a miss. At the end, we probably don't care it's a cache miss or cache hit. So it's only the time, it takes a little bit of time for us to look up the tags, and then to check if a cache hit or a miss. Then after we check that, we add a task, we add a step to this task so that we know it's a hit or a miss. Okay, so a trace is a hook that cares about tasks. So we provide a list of first-party tracers. So then those are tracers that are provided by Akita that can be used. For example, total time tracer. So by the way, most of the tracers, the first-party tracers accept a filter. So for example, if you only care about one type of task, you can filter out. You can focus on one type of task. Okay, so it includes a filter. So you may probably only care about one type of task or one type of event. So for example, total time tracer. What is a total time tracer? Well, do we even use total time tracer? We probably don't even use total time tracer. Total time tracer, for example, if we attach a total time tracer on a cache, that's the total time that this cache is handling all those incoming requests. Okay, it's the total time. So request 1 takes 1 second, request 2 takes another second. Then when we sum them up, the total time is 2 seconds. Okay, so that's total time tracer. I don't use it. It's not useful because we need to consider overlapping, right? So if we process one request and process another request and they overlap, summing them up doesn't make any sense. One place that we may care about that is whenever there's no overlap. I think it probably can be used in the ALU to calculate the ALU utilization. So like start of a calculation and end at the calculation. So that's total time tracer. Then what is the average time tracer? That is widely used everywhere. So for example, we care about what's the average latency at L1 cache level, at L2 cache level, at the DRAM level. Also from the core's perspective, what's the average latency of my memory transactions? That can tell us a lot of information. So the shorter, the better, right? The shorter the latency, the better. That's the average time tracer. Busy time tracer. So busy time tracer, it considers overlaps. So if there are two tasks that overlaps with start time and end time, we only consider global start time and end time. If there's a gap, there's something in the gap, we also discard the gap part, right? So basically that means if this component is at least processing something. So how it's used? It's only used in one position. It's at the GPU level in MGPU. We calculate the total time that we call it the total kernel time. So GPU execute kernels. A kernel is a GPU function, right? So we calculate how long time this GPU is busy, is being used. So we have a busy time tracer applies at GPU level. So we know the total amount of time that this GPU is at least running one kernel, one function, one GPU function. Okay, that's a total time tracer, busy time tracer. Okay, backtrace tracer. What is backtrace tracer? This is relatively recently implemented. So actually a very annoying thing about writing cycle-based style or even event-driven simulation is it's very hard to debug. When there's some error that triggers, then when my program crashes, my crash will print a backtrace, right? The backtrace is something like event.tick, engine.tick. Engine.tick, then is my core.tick. That's it, right? It's only two levels. I don't have much information. Why it's ticking, what it's doing, why it's crashed, right? So with backtrace tracer, because it's a tree, now we can tell, okay, when we're executing this particular task, we crashed. It will tell me this is a MMU.translation. Then all the way it's a TLB L2, TLB L1, then CU instruction. What's the instruction, right? It can tell me architecture related backtrace, so that I know, oh, we're executing this instruction, this thing failed. Okay, at least it provides more information for us to debug what's the problem. So that's a backtrace tracer. And step count tracer. Okay, step count tracer is also widely used. Remember, when I say for a cache, we calculate what's the percentage of cache hit, what's the percentage of cache miss, right? So we count every step, every type of step. Then we count how many transactions hit, how many transactions miss. So that's a step tracer. And finally, it's the DB tracer. What's a DB tracer? DB tracer is rather simple. For whatever instruction, for whatever tasks that are being traced, we store it in the database. Okay, we store it in the database so that we can recover the full trace of the MGPU execution. Okay, so those are the tracers. Then I want to show you how this tracer is being used in a real-world environment. So let's try to execute some programs, some MGPU simulations. And I want you to show how this works. I can basically play with the last two slides. You see there are two big parts. Rather than giving a slide, I would do live demonstration here. Okay, I think it's much more interesting. How I can do it? Let me start a new terminal, and I'll drag this terminal here. How I can see it? I have to look back. So It's in Daisen. Okay. cd dot dot cd dot dot. Let me check out v4. You see, v4 is our main branch, right? I just, as you can see, I didn't really prepare it. So I pretty much, I try my best at least. Every time I want to show it, it should work. Okay. Now cd dot dot. You can see in our labs repository, there's a few repositories here. Then Akita and GPU are definitely the most mature repositories. Let's run cd GPU. If I run FR samples, as you can see, the samples, these are, say, AES, FIR. Those are all benchmarks, right? So we support AES benchmark, FIR benchmarks. But let's go to FIR. You can see go build. Let me quickly run a go build to reflect the most current status. Just make sure. Go build. There's some really recent update. Now if I run the /FIR, then I can run a dash timing, dash length. I don't want to run very long. Let's run a relatively short example. Now I can run a dash report all. Okay, so Go is rather flexible with the argument type. You can either do double dash or you can do single dash. Then Go will accept both format. And for length, you can either use a space between length and 8182, or you can use an equal sign. So Go is very flexible on this argument type. Now we'll execute it. Then it's done, right? Then if I ls, you can see this metrics.csv is being created. Now you can open this file. So you can see these are the data that is being extracted from the program. And all this data are from tracers. Okay, so I want to show you what are those things. For example, driver, kernel time. This is the busy time tracer, right? Or total time tracer. I think it's busy time tracer. Then driver total time, then it's another tracer. We typically care the most about this one, but it can be also this one. This is common. It's still kernel time. So this is what field, this is where field. So just be slightly careful. This what and where cannot directly map to the what and where in the tasks. Okay, these are, say this information is extracted. Is the kernel time information extracted at the command processor. Then this is the time. The CU0, what's the instruction count? Oh, that's a tracer that I didn't mention. It's a number of task tracer, right? How many times that we executed a task is being triggered. So this task is executed 1,568 times, right? So there are many of them. Many lines. Let's go to compute unit. Then CU is compute unit. Let's keep going. It's a very long file. So here, say busy time is each CMD has a busy time. How long time is busy? This is used for ALU utilization. Then here, let me extend this part a little bit more. You can see request average latency. That's a average latency hook, right? Request average latency, that's the time. Now remember in Akita and in GPU, our time is in second unit. So those are seconds. If we keep going, you can see read heat is 299 times and read miss is 17 times. Okay, so now we can easily get a cache hit rate. Now keep going. Now at the end, we have L2 cache and also TLBs. Now, if you don't know what's a TLB, it's something that we're going to cover for the second half of the semester. Now, at the DRAM, how many transactions? What's the read average latency and what's the write average latency? Okay, those are all like right side. It's a customized tracer. But the read request latency and write average latency are every time tracers. Okay, so those are all collected by tracers. So those are different type of tracers. Now I don't want to save it. Cancel. Then let's run this. As you can see, there are many SQLite files. Those are the result of DB tracer. But let's run a new one. /far timing. I still don't want to run too long. I just want to run a short one. 192, but that's trace width. So basically, trace width is a DB tracer that applies to all the components that I know. Okay, so it will extract traces from the simulation. As you can see, rather than only printing the monitoring simulation with something, now we also print traces collected in database. So 66I50, right? So that's the SQLite 3 file. Then if I ls, you can see 66I50 is the SQLite file that we just collected. Let me go back to Daisen. Then no, there's no problem. So what is Daisen? I just want to make sure there's no update. It's the current v4 branch. What is Daisen? Daisen is a visualization tool that can help us to analyze after the simulation is completed, to analyze what exactly has happened in the simulation. So we typically find that if sometimes we find the performance is 2 times or as we expected, then why is it? We don't really know. Then I typically find the student who is doing our experiment will just tell me a guess. Then I will say, what's your evidence? There's basically no evidence, it's just my guess. So Daisen is to solve this problem, to explain or provide evidence or help users to examine what is happening in a simulation. So how to start Daisen is in this way. Daisen, and let's use, I hope this one works. Users, can I do this? Dev, SRC, GitHub, Circle Lab, MGP Sim. Then what's next? Samples, FAR. Then what's the one that we just created? This one, 66I50, right? So we start this one. Then I need to open my browser. Okay, I'm typing on this side. It's localhost 3002. As you can see. Please allow me to refresh it. Okay, the interface have some problems. Does it work if I refresh it? No, please allow me to start a new tab. No, okay, there's some problem with the, what's going on? So there are some recent code merges, so it's causing this problem. Yeah, there are some changes in the style sheet.
You can use slides, private browser.
No, it's not an extension. It's just some recent code merges that breaks the interface. It's okay. Use your imagination. Okay, thank you. It works perfectly. Now, but here, this part is the component that actually is the weird field for all the tasks. So we trace, let's say, if we look at an L1V cache, now we can search L1V cache, then it will search for all the things that contains L1V cache, right? Now I can drag this graph, drag and release it, then it will, all of them will update to create an alignment effect. Now I can zoom in by scrolling. Now it will take a little bit of time to refresh. Now you can see this is the data. So what are the data that we're showing here? For every component, we show two pieces of data. One is the incoming request rate. Incoming request rate is the start of request in task and how many of them per second. So for example, here I can see, I cannot see, is 1E8, right? The highest value, that's the primary y-axis, is the incoming request rate. 1E8, what does that mean? So remember, or GPU works in 1 gigahertz, right? 1 gigahertz, that's 1 giga is 1E9, right? So 1E9, that means if it's 1E8 or it's slightly higher than 1E8, that's basically 5 to 10 cycles, one request per 5 to 10 cycles. That's how we can interpret this data. But there are some up and downs, right? So what are other fields? Then here I'm typing average request latency. So as I can see, average request latency, what is here? 6E minus 6, right? You probably cannot see it very clearly. The resolution is low. So 6E minus 6. Then what does that mean is to E minus 9, 1E minus 9 is 1E minus 9 is 1 cycle, right? So this means is 6E minus 6 is 6,000 cycles. Really 6,000 cycles, but this is what data tells me. So it takes a very long time. I can also not see it very clearly here. So hopefully, if it's 6E minus 6, then that's the information I can read. So it takes a very long time for the every request to be handled. Okay, so what are other fields that can be processed? So we have a request completion rate. Now you can see the completion rate is these blue lines. So it's basically mirrors the request incoming rate. There should be a slight delay then, but I don't know why this seems going ahead of the incoming. But this is the how many requests that can be completed per second. Now what are others? Buffer pressure. This is actually very interesting. So see here, this value is 2E minus 1, so 0.2. So if this 0.2, that means on average around this particular time, it has fewer than one request in the buffer, right? So for every 5 cycles, there's 1 cycle that has a buffer in it. So it's just consider the cycles within this range is averaged. So how we can get buffer pressure from the trace that we collected? So all traces are tasks, no other things. Everything is task. So how we can get this information? It's basically, this is the time. Remember, this is a request in, and there's a gap between the request out and the request in. So this is request out, this is request in. So we basically, how many requests that is initiated in request out, but has not started by request in on the request inside. So it's consider this part. Then we calculate how many tasks are there. Then it's not super accurate. It maybe there's some time that it's being transferred on the network, but we generally consider this is buffer time. It's being buffered at the receiver side. Now using this way, we can calculate the buffer pressure. If some component has high buffer pressure, that means this component is not fast enough, right? So this is one way. Then never directly click this thing, okay? Always zoom in and click, otherwise your computer will freeze, your browser will freeze. So these are something that we can see that are all the tasks that are completed by this component. What is this component? It says it's L1V cache, right? So if you want to look at what's going on with this these tasks. And this task, what's the task ID? This is ID, kind is request in, what is a read request, where it happens is in LV cache 0, start is at this time, end is this time, and duration is 65 nanosecond. So 65 cycles. So then I guess that's probably 6e minus 9 rather than, or minus 8 rather than minus 6, right? So it's really blurry that I cannot read carefully, read it. So if I say, let's just imagine this is a super long instruction, and I don't know why this one is taking so long to execute. Now I can go click this task. This is a hierarchical task, right? So this is the current task. Now I can click on the parent task, then this goes to address translator. As you can see, this is address translation task, or you can do this. You can come here. These are all the address translation tasks, and these are all the memory read tasks. So address translation takes relatively short time as compared to the memory access, right? Then we can keep going up. These are at the compute unit, right? So see this one, this is a map work group, this is a wavefront, so you can consider wavefront as a thread right now. Those are all the instructions executed by this thread, okay? And this long one, I can almost tell these long ones, this one is a memory read request. Then this is a memory read request. Those are the transactions generated by this memory read request. Now if I click on it, and keep going down, as you can see, this is a reorder buffer, right? The reorder buffer is something that you know the best already. And pretty much there's nothing to reorder in this environment. Oh, this is a good example. Okay, so let's just look at what's going on here. See this one. These are Gantt charts, right? Start time and end time. Then why is nested? This is a request in. So as a reorder buffer, I receive a request. But to fulfill this request, I have to send another request to the bottom, right? To fulfill this request, I have to, so this is my parent task. I send another request to the bottom. So this is a request out. It's another request. Now you can see at this time, we send this request out. We almost immediately send this request out, right? It returns really early. I have the data at this time, but I cannot return because this task has not returned yet. So I have to wait for the first one to return. Then the whole chain can start to return, right? They all have buffer ready, but just because of the first one, it's blocking all of them, so others cannot return. Okay, so this is Daisen. Now, since we're talking about AkitaRTM, let me show you AkitaRTM really quick. So for AkitaRTM, I need to run a long simulation. Let me use a magic memory. Okay, I run the magic memory copy is I don't consider the memory copy time. That can be completed in a memory copy from the CPU to GPU can happen momentarily. Then, okay, so this is AkitaRTM. Is it done by tracer? No, this is pretty much not done by tracer. So there are some tracers there, but there are some other mechanisms. So AkitaRTM is for real-time monitoring for MGPU sim. So when MGPU sim is executing, AkitaRTM turns the simulation into a server so that we can look into the execution and see what's going on. AkitaRTM is implemented at the Akita level. So every simulator implemented with Akita can automatically have AkitaRTM. Okay, it shows it's using a little bit more than one core right now. It's using 1 GB of memory. And we can pause the simulation, restart simulation, and this is related to hung debugging. Is if the simulation is hung, it's not moving, we can force the engine to move at least one slot forward. And this is a quick buffer analyzer. As you can see, or bottleneck analyzer, we can show which buffers have big values. That if these buffers have big values, that means it's likely to be somehow a bottleneck, right? So let's see, what we can see here is L1V ROB. So we can see ROBs are generally global bottlenecks at this moment. At least somewhere below ROB is not joining requests fast enough. Now we can see by percentage or by size. This is the size and this is the capacity. Or it's automatic refreshing, we can stop refreshing here. And this one is a profiling. So we can quickly profile the simulation, taking a 1 second sample. So this is 1 second is a real time, okay? And this profiling the simulator itself is not the program being simulated. And here at the bottom, you can see the progress bar. So when there are many progress bars, I show them as bar charts. Okay, so green part is the thread that is completed. Blue part is ongoing, and gray part is not completed. And then you can go to this. These are all the components in this simulation. And you can go to CU0, and let's look at this one. Oh no, this one is not interesting. Let's look at in-flight vector memory access, and this one may be a little bit interesting. So you can check this one, and it will take a sample every second. It will send the request to the server, and request will send the immediate value, the value at that moment. So it will draw a graph. So it will, for example, I'll show you this one is more than 130, right? So it's a relatively high value. I can see it's probably a little bit bottleneck, and it's a really heavily loaded part. There are a lot of requests that are coming out, but it's not coming back yet. So the goal of AkitaRTM is to finish simulation, the analysis of the simulation without the simulation to complete. We can do some analysis while the simulation is running. So after 5 minutes, you start a simulation, we can know what's going on. If there's some problem, kill it rather than waiting for the result to complete. Okay. So AkitaRTM and Daisen are rather unique features of Akita. Then every simulator developed by Akita can enjoy this feature. Well, there are some really high values. Okay, so I think that's all for today's lecture, and that concludes the simulation part.